Hi, my name is Laura, and I'm going to talk to you a little bit about hyperbolic geometry and the Poincare Disc Model. A short disclaimer, I'm not a mathematician, but I am a very passionate amateur. I've spent the past 10 years researching this topic and learning about it under the tutelage of two professors at my university, and I'm very excited to share some of my passion with you today. Mathematician and math historian Morris Klein once wrote, "The two concepts which have most profoundly revolutionized our intellectual development since the 19th century are the theory of evolution and non-Euclidean geometry." What are non-Euclidean geometries, you may be wondering? They share the main principles of Euclidean geometry, which is the geometry that most of us study in high school. If you remember Euclid and the axioms and theorems built on those axioms and having to do proofs, that's Euclidean geometry. Non-Euclidean geometry has the same structure. It's still built on a small set of axioms. And then all the theorems in that geometry are built on those axioms. The difference is that in a non-Euclidean geometry, that set of axioms and theorems creates an alternative possibility for the shape of space. What do I mean by the shape of space? In this context, I'm talking about curvature. In mathematics, there are three fundamental types of curvature: zero, positive, and negative. Zero curvature represents a flat surface. A table, for example, or the cover of a book are both good representations of zero curvature. And standard Euclidean geometry is done in that plane. When you hear it called plane, P-L-A-N-E, plane geometry, it's referring to geometry done on a surface or in space with zero curvature. Positive curvature is, you could think of it as outwardly curved. So if you could stand on a circle and walk around on the outside, that would be positive curvature. Another good example is a basketball, a baseball, or an orange. Any spherical object that's, more or less round, not oval, has constant positive curvature. And then we have negative curvature, which would be like walking on the inside of a circle instead of the outside. It is represented sometimes by a saddle. If you think of the inside curve of the saddle, or my favorite example of negative curvature is a Pringles potato chip. Negative curvature is what we find with hyperbolic geometry. How is it different from Euclidean geometry? How is negative curvature different from zero curvature? Well, one of the fundamental ways is that the sum of the angles of a triangle in Euclidean geometry are 180 degrees. But in hyperbolic space with negative curvature, the sum of the angles of a triangle is less than 180 degrees. Another good example is that of parallel lines. One of the most famous precepts from Euclidean geometry is that if you have two lines next to each other, they will extend infinitely in either direction without ever touching, without ever crossing. On the hyperbolic plane, that isn't true. Those lines could curve away from each other, and the space between those lines would be more like the railroad tracks that you see drawn with perspective where they come to a point at the end. That's actually closer to the reality on the hyperbolic plane. Now, how can we make sense of this? Well, a mathematician from Cornell named William Thurston talks about the importance of models and the difficulty finding models for mathematics. And he likens it to trying to talk to another person about a cat, a person who's never seen a cat. We know what a cat looks like. We can imagine the sounds that a cat makes. We can hear it meow. We can hear it purr. We can hear it growl or hiss or scratch. But can we move like a cat? How accurately can we make the sounds that a cat makes? In his words, it's much more difficult to communicate a cat than to see a cat. And this is the difficulty that mathematics faces for an abstract concept such as hyperbolic geometry. And this is where French mathematician Henri Poincare comes in with his hyperbolic disk model. Henri Poincare was born in 1854 in France. He was a mathematician, a theoretical astronomer, and a philosopher. He spent most of his career at the University of Paris, where he made many, many, many contributions to pure and applied math, too many to list here in this talk. But the contribution that interested me the most when I read his biography was the contribution he made to hyperbolic geometry. And that's he modeled the hyperbolic plane with what he calls the disk model. The disk model, he took the abstract with the disk model, he took the abstract and he made it visual. He gave it visual form. To help you understand what I mean by that, if you are familiar with the artist M.C. Escher, he has a series of drawings, a series of tessellations called the circle limit series. Circle limit 1, circle limit 2, circle limit 3, and circle limit 4. Those tessellation drawings are all based on hyperbolic patterns. And the foundation, the underlying foundation to that artwork is the Poincare disk model. Why was the Poincare disk model important in the history of mathematics? Well, for 2,000 years, the Western world had assumed that there was only one geometry, and that was Euclid's geometry. And they were so convinced of its rightness, of its existence as a truth with a capital T, that Western thought began to build its foundations. Western intellectual thought built its foundations on Euclid's geometry, even the non-mathematical facets of intellectual thinking. So, for example, Descartes published proofs about the existence of God that are modeled after the proofs of Euclid. And to give you an example that's a little closer to home, the Declaration of Independence, which includes the phrase, "We find these truths to be self-evident," that also has a very close relationship to the geometry of Euclid. But once it was proven that Euclid's geometry was not the only geometry that existed, that there could be and that there are other geometries that can be proven valid by mathematics, then the major mathematical facts accepted as truths by other branches of science could no longer be viewed that way. In turn, science that relied upon mathematical theorems ceased to be truth. As Morris Klein wrote, "We no longer search for the ideal political system or ideal code of ethics, but rather for the most workable. It is commonplace to hear people say that one cannot expect perfection. This attitude contrasts sharply with those of the 18th century and the Victorian age." You might be wondering, Does hyperbolic geometry have any applications? And the answer is yes. One of the most famous is that Albert Einstein used hyperbolic geometry to prove the theorem of special relativity. It also has applications in mapping the folds of the brain, in the field of biology, in creating MRIs of the brain, in the practice of medicine, in topology of structures in physics, in the molecular structures of chemistry, and in the relationships between harmony and counterpoint in chords in the field of music. In summary, we've given attention to a mathematician less famous than some, but who still deserves a history spotlight. We've touched upon the importance of models in intellectual understanding, and we've seen a way in which mathematics is more than numbers. To learn more about hyperbolic geometry in general, or the life and works of Henri Poincare, the internet and a web browser are your friends, and you'll find plenty of easily accessible material on those topics there. To learn more about the influence of mathematics on culture, I highly recommend the series by the Great Courses called Mathematics, Philosophy, and the Real World, taught by Dr. Judith Grabiner. Thank you.